Hi, my name is Sam Lee. Today I'll present Lab 1 Constant Velocity. In this lab, the objective is to use Newton's second law to help predict an object's position at any time. And to do this, I observed and recorded a tennis ball rolling at constant velocity in one dimension. I then used Tracker on the video of the tennis ball rolling to create an experimental model of that object's movement. And then I plugged the data I got from the experimental model into GlowScript to create a computational model that allowed me to apply Newton's second law to predict the object's movement. At the end of the experiment, I compared both experimental and computational models. So to set up, I used a tennis ball, a stone countertop, and a 30 frame per second camera. The stone countertop was especially important because it provided a somewhat smooth surface as compared to a more high friction surface such as carpet or grass. And so this is the video I used in Tracker. As you can see, the ball rolls at a flat angle and it rolls smoothly. On the graph I got from Tracker, you can see it's negative. I remedied this in Excel by just changing every value from negative to positive. And this gave me a positive direction graph, so that it would be easier to compare both my computational and experimental models. So the data I got was that initial time was 0, final time was 0.667 seconds. Initial position was negative 8.896 times 10 to the negative 4 meters, and the time step was 0.033 seconds. And so I plugged, and this final time, this final time in this equation right here is just the next time step up. So that would be just the time step at 0.033 seconds. The position at that time step was 5.853 times 10 to the negative 2 meters. And this equation right here is just v equals delta x over delta t. And I got the answer for that was 1.748 meters per second. Newton's second law tells us that change in velocity is directly proportionate to F net. We know that F net should be 0 in this case, so that means that change in velocity is 0. So v is constant. And thus, our 1.748 meters per second initial velocity describes the motion of the object. So I just plugged in our experimental model values into GlowScript. So we have our initial position, our initial velocity, we have our time step at delta t, we have our final t at the max for the while loop, and then we have F net 0, and then over ball.pos equals ball.pos plus vector, I inputted 0.0577 because that was the result of multiplying our initial velocity vector by the time step, and so it would update by 0.0577 meters per time step to give us accurate results. So for the experimental versus computational model, the experimental model followed the computational model pretty closely up until about a third of the way, and then started tapering down. And the reason for this is because in real life there is friction, and so it could not follow the perfect, like mathematically perfect model completely. It always had to taper down. The velocity decreased slightly, and because of that we see the slope getting a little flatter, and it doesn't reach the position that we think it would. So what if the x's were flipped? This is the graph I would have gotten if I didn't change all my tracker values from negative to positive. But as you can see, the magnitude is equal to the previous one. The previous slide, you can see that it goes up to here. And then on this slide, you can just see, this scale is a little different, but you can see that compared to here, it's just flipped over. Compared to the computational model, it's just flipped over the axis. It just changed from positive to negative. The t values are still the same. As you can see, they start from the same spot, end at the same spot. Magnitude remains the same as well. Okay, so as for pushes and pulls, we know for sure on the y-axis that we have one pull down from gravity and one equal push up from the countertop to make F net 0. On the x-axis, there theoretically should be 0 pushes and pulls, but in this case there is friction, and friction on a rolling object is very complicated. There are many different directions it could be pushing and pulling at different times. So for this experiment's sake, we'll just say that the pushes and pulls on the x-axis are 0. So our final answer is that we know that there is one pull from gravity and one equal push up from the countertop.